Well, let's go ahead and get started. We finished up the sampling theorem last time. I'm giving you some homework. I kind of hope that you've had a chance to look at the homework. I hope you've had a chance to look at the homework, and I'm going to go over it a little bit and see if you have any questions. What I'd like to do next week, and I want to start doing this is the way that we did it when we had in class. I need you to be prepared to present your work. You need to do it either by having a whiteboard behind you or having the PDF or the LaTeX file that you use to submit the material, and I will give you screen sharing privileges, and you can walk through it. And the way I did it last time was use a random number generator. This is the way I do it in class. Anybody remember what my random number generator is?
Coins.
That's right. I randomly flip some coins. A heads is a 1, a tails is a 0, and then we translate that into binary. And so that's my random number generator. Okay. And we'll use that to choose the person that works it next time. So with that, let's go through the homework and see what the deal is. Okay, I'm going to share my screen. And okay, we're going to look at 5351. So here's an interesting problem. This starts at problem 25, if you looked at it. Is x of t equal 1 a band-limited signal? That is, if you have a signal which is a constant over all time, is that signal considered to be band-limited? Any hints? Any thoughts?
Yes, it is.
Why do you say that it is, David?
Well, you could write it as x of t equals cosine of t over infinity.
Oh, come on. So, okay, cosine of t over infinity. So in other words, the frequency is infinite. Okay, that's a weird way of thinking about it.
Oh,
I see where,
no, the frequency is, the wavelength is infinite.
Yeah, the wavelength, the period of the sinusoid is infinite. Yeah, that's one way to think about it. I think a more conventional way to think about it is looking at it as in terms of Fourier transforms. What's the Fourier transform of 1?
Impulse.
An impulse. Is an impulse band limited? In other words, is an impulse, I'm pouring myself a refreshing beverage. An impulse is equal to 0 outside of a bandwidth from minus b to b, right? So what is the bandwidth of 1?
0.
Well, yeah, it's 0, but remember we said stay away from cases where the delta function is on the edge of any interval, right? So we can say that the bandwidth is greater than 0, right? I think that would be a safer approximation. So yeah, it has a bandwidth b greater than 0. In fact, it could be considered a band-limited function for any b greater than 0. So you could have a bandwidth of 2 or 2 million, and it would still be within that class. It would be band-limited to whatever interval that you talked about in a low-pass sense. So if that's the case, then if we apply the sampling theorem, all the samples are going to be what? 1, right? So I'm asking the question, if we apply the sampling theorem and all the samples are 1, this is what we get. Is that always equal to 1? So that's the question that I'm asking. And this will take a little bit of head scratching in order to convince yourself of this, but I think that once you see it, well, once you see anything, once you understand anything, you go, yeah, I understand it. So that's what we're hoping for. Here's one that's going to require you to do a little bit of homework. And I don't mind if you work together on these, by the way, if you want to get together and work on these. Consider the uncompressed wave file. We're all familiar with compressed files, but the uncompressed file is a wave audio file. What's the sampling rate they use? I need you to look that up. I need you to find out what the sampling rate is. And then I'd like you to compare it to the Nyquist rate that we talked about, assuming humans can't hear above 20 kilohertz. I want to find out the degree to which the wave file is oversampled. And oversampling occurs, well, one of the reasons is because there's a finite byte per sample that you use. Anybody know what resolution they use on audio files like the wave file? I don't know offhand, but I'd like you to find out and find out how many bytes per sample they use. And then compare the two. I'd like you to figure out how much more quickly the wave file samples than is required by the Nyquist rate. Does that make sense? I don't see a lot of head movement. Okay, so this is going to require you to Google a little bit and to do a little bit of research. And this is something I don't know the answer to, but I think it's something that we can figure out. Now, if what we want to do is we'd like to choose a wave file that is long. There's always formatting statements beforehand and after that tells the software that it's a wave file. Then it goes actually into the meat of the program, and then there's an end, there's a stop sort of criterion. So I think it's best to choose a wave file that's long, so we don't get the waves, so we don't talk about the introductory, anybody, is there a name for that? The sort of preamble to the code before it gets into the actual data? Okay, you don't know either. So if you choose a long enough file, what's that? A header, okay. Yeah, so that the header is insignificant compared with the information bearing part of the signal. So it'll be fun to look at that and see how much faster they sample. You might be able to even find somewhere on the web how much faster they sample, how much faster a wave file is sampled than the Nyquist rate. And I'd like to know this. I don't know this. It's something I've been thinking about for a while, and I'm asking you to figure it out for me. So that's, go ahead, David.
I already did this.
You already did this?
Yeah.
Well, good for you. The homework should be easy.
I mean, I did this homework problem yesterday.
You did? For this class or for another class?
Yes.
For this class. Okay, do you want to tell, I think you can share your final result. How much faster does the wave file sample?
So it samples at 44.1 kilohertz. So that's about a little over 10% oversampling.
About 10% oversampling. Okay, so that's good. So they oversample in order to, as I mentioned, make sure that everything is copacetic, that we don't have any delta functions. If there's a sinusoid throughout the waveform, then you kind of get a pseudo delta function on an end, and so it's a little margin for error. Did you figure it out this way, David?
I'm not quite sure what.
In other words, I give you a procedure here. What is the sampling rate used compared to the Nyquist rate? Do you know what the byte size for each sample is?
Yeah, I found on Wikipedia that it's 2 bytes per sample.
2 bytes. So that's 2 to the 16th, which is what?
Yeah, 64,000 so.
Okay, so yeah, 64,000 quantization levels, right? Mm-hmm. So that's pretty fine-tuned, isn't it? What do you think would happen if we decrease the byte per sample? What do you think it would sound like? Anybody have any idea? If we went down to, say, half a byte per sample instead of 2 bytes per sample.
It would sound kind of like auto-tuned, I guess. It forces it into different levels.
Well, it would force it into different levels of amplitude, sure. I don't know if it would force it into different levels of frequency, though, because the coding is not done in frequency, is it?
You're right. I see what you're saying. I guess I was just trying to find a way to describe it. But yeah, force it into the amplitude levels.
Yeah, it would quantize into the amplitude levels, and I'm not sure exactly how that would sound, but clearly it would be a distortion over the original signal. Okay, so that's a nice everyday signal, and now David has given us a ballpark of what you should achieve once you find this. So make sure you cite your sources here. If you would. 27 is, we know from Parseval's theorem, the equation which is shown here. This is something that we proved last lecture. Do you recall that? We proved Parseval's theorem. And so is the following also true? Now, Parseval's theorem requires the integral of the magnitude squared. In other words, the energy of the signal. And that is equal to 1/2b times the sum of the energy in the samples. Is the following true? The integral of the signal, is that equal to the sum of the samples? Now, you'll notice in order to maintain the dimensions that the left-hand side, I'll go down here and highlight it. I think I'll go down here and highlight it. You see that the left side of this equation highlights a t. So this has units of volt time, if you will, volt seconds, or volts per hertz, right? Whereas the right-hand side also would have units of volts per hertz, since B is a bandwidth. And if this is true, why? If it's not true, why not? Can anybody figure out the way that we could figure this out?
Let's see. So I found that equation in the textbook, and it was referred to a couple other equations, but not to Parseval's theorem. So I got most of the way to confirming it from those equations, but I think there was some error somewhere, so it wasn't looking quite right.
Okay, let me tell you an easier way instead of plowing through equations. Go to the original cardinal series. Let's see, do I have it here anywhere? Where's the cardinal series? Cardinal series. Okay, we don't have the cardinal series here anywhere. The cardinal series says that, I'll just give the cardinal series here. I think this should be something very easy to do. Don't erase what I don't want you to erase. Silly Google Docs. Okay, so that's the cardinal series, right? And it's very nice because we can write it without too much hassle. A nice sink, there's no sine of pi x over x or anything. So that's the cardinal series. Now, let's look at this and let's look at this. How can we get this from this? Wish I could put that in front. I don't know if the math will let me though. Yeah, it'll let me, okay. I just have to be persistent. There we go, that's a cardinal series. Okay, we have this, right? Well, we have this equation, right? We want this equation. How do we get this from the cardinal series?
So by integrating both sides?
Integrating both sides. Now, if you integrate both sides, the integral on the left gives you this, right? What does the integral on the right give you? Well, if on the right, you can take the integral side through the summation sign, through the samples, and just integrate the sinc, right? Integrate the sinc over all values of time. Does that make sense? Okay, it's okay if you respond. I know we're on Zoom and I can't hear you all, but so I need some visual cues that to my online queries. And yeah, if we integrate both sides, maybe we'll get this. And we already know how to integrate the sinc, right? Yes, you know how to integrate the sinc from the integral property of Fourier transforms. So you should be able to indeed show this. So I gave away the answer. I didn't mean to. I was trying to be discreet, even though I'm continuous here. I was trying to be discreet, but I didn't make it. Yeah, this is true, and you need to show it.
I have a question.
Sure.
So the magnitude sign on the functions, I actually don't really understand what that's doing to the function. So if I'm guessing if you have like an imaginary, then that goes away. But then if you have like a negative part in your function, does it turn positive, or what's that absolute sign actually doing to the function?
Okay, that's a fair question. Yeah, stupid automatic capitalization. Yeah, here's the truth. The magnitude squared of anything, let me just do it this way. It doesn't even have to be a function. Z, if I take the magnitude of Z squared, that is equal to, by definition, and this is the way the mathematicians write it, is equal to, by definition, Z times Z conjugate. That's the definition of the magnitude squared. And so you can see if we have a real function, then the magnitude squared is the same as just squaring the function, right? But we're allowing here for complex signals, so we do have the conjugation. And there do exist a lot of places where you have complex numbers all over the place. So, or complex functions, so we need to be careful about that. By the way, when you write papers, I don't know if you knew this, but when you end an equation that ends a sentence, you need to put a period after it. You notice where Z is equal to Z times Z conjugate, period. That's the end of a sentence. So a period belongs there. And then a new sentence is started. Is the following also true? Now this is actually a sentence, isn't it? And what's the verb in the sentence? The verb in the sentence is equal to, right? Is a verb, correct? Is equal to, and so that's a complete sentence. So that has a period that belongs to it also. You'll notice in well-written books and math, they always are consistent with the putting of the periods there at the end of sentences. When an equation ends a sentence or an equation is a sentence. A lot of people don't do that. There's not a lot of consistency, but indeed that's the thing to do. Okay, so hopefully that helped some things. Did that answer your question, Aiden?
Yes, thank you.
Okay. Okay, here's going to be a little bit trickier one. I'm asking you to show that the following is true. Oops, put the sentence period in the wrong place here. And that is the following. If you sample the derivative. Now here's a question. If a signal is band limited, is its derivative also band limited? What happens if you differentiate in the time domain? What do you do in the frequency domain?
And you just multiply by a certain expression. I'm forgetting
J2 pi u. You just multiply in the frequency domain by J2 pi u. So I've hidden my self view so you can't see me now. That's probably wasn't a good idea. So I'm going to re-show myself.
We can see you.
You can see me?
Mm-hmm.
How do I look?
You look happy.
Okay, good. Okay, so therefore I can't see myself though. I got to see myself to make sure that I'm on screen and stuff like this. Well, that's what I get by trying to look nice here. Okay, I'll fake it out. The idea is that if you have a band limited signal that's 0 outside of a certain interval from minus b to b, if you multiply it by J2 pi u, is it still 0 outside of the interval from minus b to b? Of course it is. Again, if you have a signal that's equal to 0 outside of minus b to b and you multiply it by anything, it's still going to be 0 outside of the interval of minus b to b. So yes, the derivative is also band limited. So we can take the derivative of the signal and we can sample it and then interpolate the derivative, can't we? Right? And what about the second expression? That is the expression that's shown here. Well, we could also do the cardinal series and differentiate the cardinal series, can't we, and get the derivative? So we can interpolate samples of the derivative, or we can differentiate the original cardinal series. Okay, any questions on that, or are you totally opaque? Okay, I just added my self view so I can see my lucid features again. Any questions? Take a look at that. Again, let me repeat it. Here you can interpolate the samples of the derivative and use the samples of the derivative to generate the derivative of the signal. Or over here, you could take the original cardinal series. The original cardinal series was where? Right here. You can take this cardinal series and you can differentiate it. What happens if you differentiate the left here? You take the derivative past the summation sign, you take the derivative past the samples, and you're only operating on the derivative of the sink. Right? And how do you think the derivative of the sink would look? First of all, the sink is even. What do you know about the derivative of an even signal?
It's odd.
It's odd. And so the derivative, I'm trying to switch things for your view. I think I got it wrong. The derivative is an odd signal, so it goes like this, okay? The derivative of the sink. But you use the derivative of the sink as your interpolation function, and that works also. So that's an interesting result. This was motivated by a question asked by Athanasius Popoulas in one of his homework problems. Okay, I'm giving you big fat hints here. I hope it's okay. Okay, now I'm going to show, this is 29, show that if a signal is sampled at a rate greater than the Nyquist rate, then the sampling theorem can be written as the equation here, where R, which is known as the sampling rate parameter, is equal to the ratio of B over W. Now, in order to do this, I'm going to share my screen and go to the whiteboard. Okay, there were my previous posts, which nobody wants to see. And here's a little bit of hint about how to get this, okay? We start with the cardinal series, x of t. Now we're going to oversample it. We're going to oversample it. Now, what does it mean by oversampling? That means in the spectrum, if we looked at the spectrum of this, the spectrum would still have a baseband signal that went from minus B to B. But we're oversampling. So the oversampling is at a rate of W, which is greater than B. So therefore, we're going to have something which occurs like this. We're going to have humps which are separated by quite a bit. Does that make sense? That's because we have oversampled in order to avoid aliasing. So we have these little gaps here. We showed last time that if we lost a sample, that we could regain that sample by looking at what happened to the interpolation in the gaps. We're going to do something a little bit different. If this is a signal x of t, what we're doing is we're assuming that signal is 0 outside of this interval from minus w to w, right? So this is the period that we're duplicating. So we're duplicating these humps with white space on both sides. Recognizing that this signal x of t is still band limited from minus b to b, correct? So if I take this Fourier transform of this signal, and I multiply it by a rectangle that just goes from minus b to b, in other words, I multiply it by this rectangle. Am I still going to get exactly the same result? Sure, I'm going to get exactly the same result. But this says, if we inverse transform, this says that x of t is equal to x of t convolved with the inverse Fourier transform of the rectangle function, which is the following. Right? We multiply in one domain by the rectangle we convolve in the time domain. Is good? So this is equal to the oversampled signals times the sink of 2wt minus n convolved with 2b sink 2bt. So this is equal to x of t, and I've convolved it with 2b sink 2bt. So the question is how does this simplify? And that's the question. And you have the tools in your toolkit to simplify this expression. Probably the easiest way is to Fourier transform, multiply the two transforms, and then inverse Fourier transform. You notice this first one is going to give you some stuff times a pi of u over 2w. Okay, this is going to be stuff. And what is this one going to give you when you Fourier transform? It's going to give you some more stuff. Times pi of u over 2b, right? So again, this is going to give us a rectangle of u over 2w. This is going to give us a rectangle of u over 2b. And so we're multiplying two rectangle functions. Well, guess what? One of these rectangle functions goes from minus w to w. That's this rectangle function from this sink. This rectangle function goes from minus b to b. And if we multiply these two rectangle functions together, one of them no longer becomes viable, does it? In fact, this thing goes away. We don't even need this anymore. It chops that off from minus b to b. So that's the trick. Fourier transform, it recognizes that the u over 2w goes away and inverse transforms it. If you do that, you will you will obtain the expression that is given in the homework problem. Does everybody have this idea?
So I have a question.
Yes.
So basically, you know that when you multiply them together, that in the frequency domain, part of it cancels out, basically.
Well, yeah.
And so
Yes.
And so what you said is you need to realize that they cancel each other out in some parts in the frequency domain. And that also translates to the time domain. So you can Fourier transform that, then get rid of some stuff and then inverse Fourier transform it.
Yes, exactly. So this is going to be, this stuff times pi over u over 2b, right? Whoops. In other words, that pi of u over 2w totally goes away. Now, what is this stuff?
Yeah.
Okay, these are constant times e to the j stuff. This is constant times e to the j stuff. So when you inverse transform it, you bring along the constants, and then the e to the j stuff gives you a shift. Good?
Yes, thank you. I was confused at first, but I forgot that the left side is just x of t. So you also would do it to that side, but since it's just x of t, it doesn't really matter.
Yeah, it's an identity. It's a curious way to think about it, but yeah.
Yeah, that totally makes sense. I got it. Thank you.
Okay, good. Thank you. So going through that exercise that I just outlined, you should be able to derive this formula where R is equal to B over W, which is something which is less than 1, because W is always a sampling rate that exceeds the Nyquist rate. So B over W is always going to be less than 1. We good? Then I'm going to ask you the same question as before. If x of t is equal to 1, is it a band-limited signal? Yes, it is a band-limited signal. We've already answered that. If so, is this signal, in other words, if we set all of the samples here equal to 1, is this always going to be equal to 1 for all r greater than, or all w greater than 0? Anybody want to hazard a guess?
Yes, I actually tried, did some experiments in MATLAB for the previous question, and found some nice answers, or found some nice plots.
Okay, so do they corroborate the conclusion that I gave?
Yeah. Basically, well, you have finite samples and finite bandwidth. The you get a approximate rectangle function of finite width, and you expand and it gets wider.
Oh, okay, that's interesting. Do you have plots for that, or?
Yeah.
Well, I tell you what, let's take a chance and see what you got here.
Right. Let's see.
Go ahead and share your screen, David, if you wouldn't mind.
Yeah. Let's see. Oh. All right. So.
So you're a real-time programmer, I guess, right?
Yeah, I've done a lot of programming at work. Okay, so yeah, here's the plot.
Well, that looks like Gibbs phenomenon. That doesn't look like. Okay, go ahead.
Yeah, so let's see. So, right.
So this is the summation of a finite number of sinks?
Yeah, I can, well, yeah, well, in MATLAB you can't, yeah. So from t is minus 100 to 100 with a b of 1, and n from minus 20 to 20, yeah, you get this kind of approximate rectangle function, and as you increase the range of n, like
if you increase the range of n, you have the same thing, which except now it goes to 100. It has a full range of 100.
Yeah, actually,
So
the previous was actually the previous one was zoomed in from 100 to 100, looking closer at the rectangle function, and so now the rectangle function is wider than it was before, I think.
Okay, because you've used more sync terms. Okay, thank you, David. Thank you.
You're welcome.
Go ahead and unshare your screen now.
Okay, yeah, let's see. I'll see. Oh, okay, yeah, there.
Okay, good. You know, one of the things, let's see, I want to clear all drawings. Okay. One of the things that's interesting here, let me elaborate on this, is that we're asking ourselves, if we sum a bunch of sinks, well, that's not very good. If we sum a bunch of sinks, and they all have a value of 1.
Okay.
This is another way to look at it, right?
Yeah.
And I think this was exactly what David was doing, if I understand. Remember that beautiful interpolation property that we had with the cardinal series? Well, just assume, I think you can see that the mathematics says is that we have a value of 1, right? That these add up to 1.
Yeah, at least
that's a bandlimited
integers.
signal. Yeah, now if you look at B, what if you take these, what if you take this thing, this is on a rubber band. Let's say the t-axis is a rubber band. What happens if you stretch that rubber band? If you stretch that rubber band, then you get a bunch of sinks which are really spread out far, right? But you know what? They're going to add up to the same thing. It's just like taking one. It's just like taking one, which is the interpolation of all of these things. It's just like taking one and stretching it. If you take one and you stretch it, you still get one, don't you? Right? So it doesn't matter how wide the sinks are. It doesn't matter what B is on the interpolation. So it's kind of a cute relationship, a cute idea. Similarly, if you crunch these down and you have really close sinks, I probably won't be able to do this justice. But if you have really close sinks, right? Okay, I'm right. I don't do that justice. But if we were to take these sinks and we were to shove them in together, they would still all add up to one. So it's an interesting kind of picture of what is happening here. Okay, let's go back to sharing the screen here. Now here's what I want you to do. An equation 30. Using problem 28, prove that the sample at the origin can be found from the known samples by this equation. In other words, this is a lost sample equation, and it's different from the one that we derived in class previously. But it says the sample at the origin can be regained from the remaining oversampled values, except for the value at n is equal to 0. So on the right here, we have all of the known samples, and all of these known samples can be added up to give us the samples on the left. Now, how would you do that? I'm going to tell you, and please listen. You can divide this summation up into the n is equal to 0 and the n is not equal to 0 side, right? You can divide this sum into the n is equal to 0 term plus all of the n is not equal to 0 term. Then you can take the n is equal to 0 term to the other side. Well, first of all, what you want to do is you want to set t is equal to 0. I got ahead of myself here. You want to set t is equal to 0. As soon as you set t is equal to 0, you can divide the summation into, again, n is equal to 0 and n not equal to 0, and then solve for the x of 0. And you should be able to get this equation here. So this is how you recover the sample of the sample at the origin if you lose it from all of the other samples, according to the sampling theorem, if you oversample. Now, can anybody tell me what happens if we sample at the Nyquist rate? If we sample at the Nyquist rate, then all of the samples are independent of each other in some sense, correct? So if we lose a sample, that's tough luck. We've lost a sample, nothing we can do about it. But what happens to this equation? Does this equation says I can still regain the sample from the samples remaining? Can anybody offer a hazard guess from what we've talked about so far?
Wouldn't R equal 1, and then you have an issue with the coefficient?
That's right. That was Aiden. Yeah. Okay. Yes, exactly. Well, if the sampling rate is equal to the Nyquist rate, then B over W, R, if you will, is equal to 1, right? What happens to this equation when R is equal to 1? Well, it's no longer functional, isn't it? It doesn't work anymore. The other thing that gives us a clue, we won't go into the definite mathematics of it, but I think you can see it. What if R is or what if the sampling rate is just a little bit above the Nyquist rate, say 1.001? So it's just a little bit above the Nyquist rate. What is this R going to be? It's going to be a very small number, right?
Mm-hmm.
Or no, yeah, no, R is going to be like 0.999 or something like that, right? What happens to 1 minus R? 1 minus R is going to be a very small number. It's going to be 0.001, right? If 1 minus R is 0.001, then that means any mistake that you make over here, if you have a little bit of noise, that noise is going to be amplified by 1 over 0.001 or by 1,000, if you will, and you're going to get a lot noisier interpolation. So you can see that the greater that we sample over the Nyquist rate, at least intuitively at this point, the more noise immunity we get in the lost sample restoration. So again, let me repeat that. If W is very close to B, say it's 1.001 times the Nyquist rate, just a little bit above the Nyquist rate, then the 1 minus R is 0.001, and this 1 minus R in the denominator of this formula is going to be 1,000. So everything, whoop, okay. So everything in the formula to the right in the summation is going to be magnified by 1,000, and any errors that you make there are going to be magnified in estimating the lost sample. So we get no free lunch. You just can't sample greater than the Nyquist rate and restore it, because you do get this noise sensitivity that gets better and better as you increase the sampling rate more and more. Okay? So that hopefully gives you insight into these problems. Are there any questions on any of these problems, which we'll have due next Tuesday? And again, be prepared to have something that you can share on your screen if you are called on to make the presentation. Also, I have no qualms about if you guys work together. You know, if you want to work together to solve any of these problems. Any questions at all?
I am curious about question 32.
What do you think?
Yes.
You know why I put 32 there? Because I want to maintain the list here. And I think if I erase it, I got to jump through a hoop in order to get the 32 back here. So no, seagulls do not burp. In fact, nobody should use this, but if you wrap up an Alka-Seltzer, everybody knows what an Alka-Seltzer is, right? If you wrap up an Alka-Seltzer in bread and feed it to a seagull, the seagull will get sick and die because it can't burp.
So I looked into that, and a lot of places were saying that's an urban legend.
Okay. I'm going to have you talk to my brother. I won't say that he did it, but because I don't want to give any evidence for cruelty to seagulls. But I have evidence otherwise. So okay, we deviated a little bit. That's enough. That's enough. Okay, you do not have to hand in nor address the question asked in 32. Any more questions other than 32? Okay, hearing done, I'm going to go on with the lecture for about, I don't know, it looks like for about 20 minutes. And we're going to jump over to a new chapter. Lucky you. I'm opening up PowerPoint, and this is going to be kind of low tech at this point, but I think you'll enjoy this. We're going to go into multidimensional signal analysis. And one of the beautiful things about multidimensional signal analysis is many times we can recognize things in lower dimensions and we can generalize them to higher dimensions. And there is a beauty in that because it allows us to do geometrical interpretations in lower dimensions. It gives us intuition of what to do to higher dimensions. And if we're concerned about that, we can always go to the mathematics to prove our intuition. One of the books that changed my life was a book called Flatland. How many have heard of the book of Flatland? It's a great book. It was a book written in 1881 by a guy named Edward. Abbott. I don't know if his name was Edward Abbott. Yeah, I guess it was Edward Abbott. And it was called Flatland, and it was a romance of many dimensions. I read this when I was in college. I think I was a junior. And it's right before I became a Christian, and it kind of woke me up. It's kind of on my top 10 books. And maybe it's why I do multidimensional signal analysis today. But it's the story about these people that lived in Flatland, and they lived on a plane. They lived in 2 dimensions. And it is how they took their ideas and their observations in 2 dimensions and extrapolated them to 3 dimensions. So here's a quote from it, and I'm not going to read it. But here's the interesting thing, and I'm going to get back to this in a second. But my Lord has showed me the intestines of all my countrymen in the land of 2 dimensions. Would you like to see the intestines of all of your countrymen? Well, we're going to argue that if you were in 4 dimensions, you could see the intestines of all your countrymen. Are you excited about that? Anyway, this was with Flatland. Okay, here's the basic story about Flatland. The Flatland existed in just 2 dimensions, and everybody knows about 2 dimensions. And there was this square. In fact, you notice, what was Flatland written by? It was written by A square, right? So he was a 2-dimensional square that lived in Flatland. And he went around and made these observations. And one of the things that existed in Flatland was line land. And line land consisted of a bunch of line segments. And these line segments, they couldn't cross over to each other, so they kind of communicated through a telephone wire to each other. And the interesting thing that the square noticed is that these lines had no idea what was happening in Flatland. Line land had no idea of what happens in Flatland. And the other thing he noticed, which was really interesting, I think I have some animation here, so maybe I should pop it up here. So that was the case. And then also in Flatland, there was something called point land. Now, point land was just an entity unto itself. Point land just existed, and everything that happened, point land thought, it's me. This is the universe. This point is the universe. I am so cool. Wow. And if anybody tried to communicate to him externally, point land would go, oh, I'm so wonderful. I'm so wonderful that I was able to generate that voice that I just heard. So that was this total universe. So that was the idea of a square. Now, the square decided to get together at a meeting, and he gave this theory of up. And the theory of up was that there was a dimension which was orthogonal to the 2 dimensions. And of course, we know it was the 3rd dimension. But all of the people at the scientific conference, they said, I'm butchering the plot just a little bit, but I'm putting it in the parlance of engineers and conferences and stuff. But all the people said, okay, which way is up? Okay, yeah, which way is up? Point to up, which way is up? And the best that a square could do was point north. He said, well, it's this way. And he pointed up. I think today when people talk about heaven, they say, which way is heaven? And they go, well, heaven is, it's up, okay, instead of north. I thought there was a parallel there that Abbott was making. And so anyway, they were discredited. A square was discredited with his theory of up and other dimensions in the 3rd dimension. But then there was a visitation by a sphere. And the sphere came and it said, hey, I've been watching you. So it had a visitation to the square. I came one too early. And it says, I've been watching you from the 3rd dimension. And the square said, oh yeah. And the sphere said, yeah, watch this. And all of a sudden in front of him, the square saw a little circle get bigger, and then the circle got small, and then poof, it disappeared. And what it was the sphere passing through the plane, okay? And he said, wow. He says, so there is a 3rd dimension. I was right. And the sphere said, yes, you are. Would you like to see it? And so a square said, yeah, I'd love to see it. So the sphere picked up a square and it took him off the plane and rose him up so that he could actually look down on Flatland. And he was amazed. Now, remember we talked about intestines and seeing the intestines of your countrymen? Think of all these guys. They had intestines inside of them, right? And they had a stomach which was full of the two-dimensional peanut butter sandwich that they had for lunch. And the square could see inside of the people, right? He could see the intestines. It was kind of disgusting, but he could see it. And they flew around and he thought, this is really, really cool. And so the square made a request. He said, this third dimension is really, really exciting. It's really, really great. Show me the fourth dimension. And you know what the sphere's response was? There can be no fourth dimension because a fourth dimension would have to be in a direction which is orthogonal to the three dimensions that we have here in space-time, or four dimensions if you include time. And so the sphere says there is no fourth dimension. So the sphere was suffering from the same limited thinking that all of the audience of the square was below. All they could comprehend was their current environment and the history of what was going on. So this, I thought, was amazing. So it made me think, my goodness, there might be a fourth dimension. And we hear today of scientific talk about fourth dimensions. Another place this appeared was in H.G. Wells's book, The Invisible Man. I think there was a recent remake of The Invisible Man, which was very different from the H.G. Wells book. But when he wrote The Invisible Man, there's a passage in there where the Invisible Man, the guy that turns into the Invisible Man and eventually goes mad, he says, I have found a general principle, a formula, a geometric expression involving four dimensions. And this was very interesting. And today you hear of possible parallel universes where there's a number of three-dimensional universes packed side by side. Physicists talk about this like it's a reality. And then there's string theory, or M theory. And the string theory and the M theory believe that in strings, you know, strings are really small. I don't know if you know this, but what they've done is they've abandoned particles and they've gone to strings, which are little things that vibrate, And they're so small that if you took a proton, you know how big a proton is? That's really little. And you magnified it to an inch. Or no, I'm sorry, if you took a string and you magnified it to an inch, you would take the diameter of a proton and expand it to several light years. Think of that. If you took a string and expanded it, they exist on orders of Planck lengths. If you expanded it to an inch, it would, that's equivalent to taking the diameter of a proton and expanding it to several light years. So you can see that strings are really, really small. And that's one of the reasons that they've escaped any sort of experimental verification. But string theory, which is yet unproved, and it looks more and more like it will never be proved because of these constraints. We can't get down that low. We can't get down and measure strings. We can only see consequences of them at all. All the attempts thus far to measure the consequences of string theory have been futile. But the idea of string theory has compactified dimensions. What is a compactified dimension? They have 26 dimensions, or at least when I read it, the account I read for it, it says that they had 11 or 26 dimensions. What is a compactified dimension? Well, if you think about a sheet of paper, and I have a paper towel here, which I'm going to use as a sheet of paper. If you think about it, a sheet of paper, how many dimensions is that? That's kind of like 2 dimensions, right? But if you take this and you scroll it up and you look from very far away, it kind of looks like 1 dimension, right? Those 2 dimensions have been compactified into 1 dimension. So string theorists say that yes, in these strings we have these compactified dimensions. Why do they do it? Because it makes their beautiful, beautiful theory work. I had a friend who was a doctoral student in physics that specialized in string theory. His dissertation was in string theory. And one of the beauties about the theories of today is that they are so precise. If you think about it, all of the major equations of physics and relativity and quantum mechanics and everything fit on a single sheet of paper. That's really astonishing if you think about it. And the beauty about string theory is it's so eloquent. It's a very compact, very nice represented theory, which has incredible explanative powers. So yeah, on the sheet we would have things like Newton's equations and the theory of special and general relativity. We would have quantum mechanics. We would have Maxwell's equations. We would have all of the fundamental theories of physics, and they could all fit on a single sheet of paper. And this is one of the beauties of string theory, is that it's so eloquent. And my PhD friend, he says, this is such a beautiful theory that if it isn't true, it should be true. If it isn't true, it should be true. It's just so beautiful. But unfortunately, it looks like string theory might never be proven. You never say never, but it turns out that all attempts thus far to prove string theory have been futile. Stephen Hawking, in his book, A Brief History of Time, talks about creations of universes. And he talks about how fortunate we are to live in a three-dimensional universe. It could be that when the universe was created, it could have been 2 dimensions, it could have been 6 dimensions. At least these are possibilities in the theories that people that do these theories talk about. And you know why he said you couldn't have a 3D, why it was fortunate that we had 3D instead of 2D? He said, look at a dog. If we had a dog and we had 2 dimensions, that dog would have a problem because dogs eat and then they do their thing, right? That you have to pick up with a pooper scooper. And all of that is one long channel. It's one long tube inside the dog. And Stephen Hawking said, you got to have that long tube inside the dog. Otherwise, if you had this channel from where you eat to where it comes out, you would have problems. And you would have, the dog would drift apart, according to Hawking. I think that's kind of inane. I think that maybe we could have dogs which are kept together by little magnets or something like that. But this is all speculation, and it was very, very interesting. So let's talk about some properties of higher dimensions. I want to check my time here. Okay, we have a few more minutes. Imagine that you're always a right-handed person in 2 dimensions. You see all these hands? These are all right hands, right? And if you're constrained to 2 dimensions, you're going to move around these right hands, and you're always going to stay and be right-handed, aren't you? Right? Nothing you can do about it. But if you had access to 3 dimensions, what could you do? You could flip around a right hand to be a left hand, couldn't you? Right? If you had access to 3 dimensions. You could make a right hand into a left hand. If you had access to 3 dimensions, you would go out of the 2-dimensional space into 3 dimensions, flip that thing around and come down. Think of the consequences of that generalization to 3 dimensions in the sport of baseball. And this is literally true. It's amusing, but it's true. Say we had a left-handed batter, and this left-handed batter was coming up to bat, and he was facing a left-handed pitcher. Well, I think that's bad, right? So you'd prefer to have a right-handed batter. Well, if you had the 4th dimension, you could take this baseball player, flip him into the 4th dimension, and bring him back as a left-hander. Let's see, I guess this is the left-hander, this is the right-hander. So you could flip a baseball player and come back and have him bat right-handed. Of course, all the lettering on his uniform would be backwards. And of course, the other team could flip their pitcher around and make a left-handed pitcher into a right-handed pitcher if we had access to 4 dimensions. But we don't, but this is something that would happen if we did have access to four dimensions. Okay, another interesting, I think these are just fascinating, interesting. So if you had chains in Flatland, now this is a chain in Flatland. We're restricted to 2 dimensions, and can you see one of these green things can't be separated from any of the other green things if we constrain ourselves to be in 2 dimensions, right? They would just bump into one another. So this is a chain, this is a two-dimensional chain, and it will remain a two-dimensional chain as long as you're constrained to 2 dimensions. But if you had access to 3 dimensions, what could you do? You could take this and you could flip it around. You could raise it off of the plane, then come back here and redeposit it and do an unlinking of the chain. Do you see that? If you had access to 3 dimensions? Now, does this mean that in 3 dimensions, if you had a chain that was locked, if you had access to the 4th dimension, could you unlock it? And the answer is yes. If you had a 4 dimension, you could unlock a chain in the conventional sense. And the interesting thing about this, I think, is a passage from Scripture. And the passage from Scripture talks about chains linked in 3 dimensions were separated. In Acts 12, read, the night before Herod was to bring him to trial, Peter was sleeping between 2 soldiers, bound with 2 chains, and sentries stood guard at the entrance. Suddenly an angel of the Lord appeared, and a light shone in the cell. He struck Peter on the side and said, and woke him up. He said, "Get up, quick, get up," he said, and the chains fell off Peter's wrist. Okay, now, could this be the explanation of the miracle, the access to the 4th dimension? It could be. Is this the explanation of the miracle? I don't know. But it's kind of a fun way to think about it, isn't it? It's an interesting way to think about the 4th dimension. And if we did have access to the 4th dimension, how we could do miracles such as unlinking chains. Walking through walls. Suppose you were in a box in Flatland. Here you are. You're a smiley face with a tongue sticking out. And you are in this 4 walls. If you constrain yourself to be in 2 dimensions, you can't get out, can you? However, if you have access to 3rd dimensions, you can get out. You just lift yourself into the 3rd dimension and you are out of the jail. Does this extend to 3 dimensions? And if it did, does it mean, what does it mean? Does it mean we could walk through walls? Yeah, we could walk through walls if we had access to 4 dimensions or a higher number of dimensions. And this is also something that we are reminded of from Scripture. John 20:26 says, a week later his disciples were in the house again and Thomas was with them. Though the doors were locked, Jesus came and stood among them and said, "Peace be with you." So therefore the doors were locked, so Jesus must have come through the walls. Or they didn't explicitly talk about the roof or the floor, but I think those are implicitly excluded. But anyway, if they had access to if Christ had access to the 4th dimension, he could indeed do that. Again, I want to emphasize, could this be the explanation of the miracle? Yeah, it could be. Is it the explanation of the miracle? I don't know. So I don't want to present this as the definitive explanation of the miracle of walking through walls. But nevertheless, it's a fun illustration of the idea of things that can happen in 4 dimensions. Okay, I think that we'll probably stop there. I think this was a fun introduction. I hope you found it fun thus far into higher dimensions of the things that can happen in higher dimensions. And one of the things I want to take away here is that we can see things which happen in 2 dimensions, and if we're allowed 3 dimensions, we see the consequences of what can happen. And then we can extend that to 3 dimensions and see what happens in 4 dimensions, whether it be breaking chains, walking through walls, or something like that. Right? So that's the takeaway. That's the serious part of this, is that our geometrical interpretation in lower dimensional spaces is applicable to higher dimensional spaces, and we can extrapolate in an incredible way to find these things. Okay. Any questions at all? Okay, yeah.
About the string theory, I have been told that there are like 10 to the 900 or so like free variables that can be adjusted however you want. So it's I've gathered from that that it's not as elegant as.
Okay, I am not an expert enough in string theory to comment. I can comment about a student of Gerald Cleaver, who is our man at Baylor, who is into string theory. One of his PhD students told me. He said, it is so beautiful and eloquent. If it isn't true, it should be true. So I can't comment on the 900 variables. I do know that I've seen criticisms that, yeah, you can do almost anything with string theory, but again, I don't have the expertise to comment on that. Wish I did. Okay, any other questions? Okay, thank you. We will talk next time, and I will call on you randomly to work the homework problems that have been assigned. Thank you for your attention.